Okay, folks, I had a few of you ask about this question here, so I thought I'd go ahead and do a quick video of it. So this is a basic radioactive decay problem, and it's probably similar to one that you've worked many times before. So I'm not going to spend a whole lot of time on the solving of the differential equation, or even really the setting up of it. The real issue is how they give you the information to figure out what percentage of the current amount of U-238 you have. So that's kind of a strange way of posing the question, but it's actually more realistic in that you would do some sort of sample analysis and you'd find out what percentage of this substance is the U-238 and what percentage of the substance is lead. And so it makes sense to talk about it in terms of a ratio, but that's a little bit confusing, and that's going to be the challenging part here. So if you're having trouble with setting up the differential equation, feel free to let me know or take a look at some of our other applications. This is kind of the wrong problem to start with that on. So because this is a radioactive decay problem, we know we're working with the differential equation y prime is equal to ky, and I like to just use a positive, or I like to just use the symbol k, and then we will see in this case that the sign on k ought to come out to be negative if this is radioactive decay. So without further ado, we can go ahead and solve this differential equation by separation of variables. So we've got dy over y is equal to k dt, and then we integrate both sides with respect to their variables in this sort of shortcut technique that we learned. And we get the natural log, the absolute value of y, is equal to kt plus c. And then doing our little rigmarole magic that we've done many, many times before, we get ce to the kt. So I don't think that was the part of the problem that was too difficult. And if you're having questions with this, I'm going through it quickly, so please let me know if you're having questions with this part. The next issue is we need to figure out what k is. Well, scientists like to sort of encode the information for k in a nice, easy statement called the half-life statement. So rather than giving somebody the number k, they tell them the half-life, and it's very easy to solve for k once you have that. So we know that after 4.51 times 10 to the 9th years, we should have half the amount of uranium-238. So one way to do that is to set, we know that we've got this ordered pair here, 4.51 times 10 to the 9th, that's our time value, and we would have half of our original amount, so half of our C naught, or just C. So I'm going to plug this in for y, and I'm going to plug this in for t, and so that gives me 1/2 C is equal to Ce to the k. We still don't know what that is, that's what we're solving for, 4.51 times 10 to the 9th. So solving this for k, we get, well, first we can divide out the c's. That's why we're not told the original amount of substance, and we can then take the natural log of 1/2. That's going to be equal to k times 4.51 times 10 to the 9th, and so we get at long last k is approximately well, actually k equals the natural log of 1/2. Let's write that a little better. 1/2 over 4.51 times 10 to the 9th. And well, the directions for this problem say to not round into the very end, so I'm not going to actually, I'm going to use this in my computation when I do my final computation, but just to give you an insight, this is approximately, I got minus 1.537 times 10 to the minus 10th. And the biggest thing that I just wanted to point out there, of course, is that when you take the natural log of half, you get a negative number, and the sign on this k value is negative, as we expected, because this is a radioactive decay problem. Great. Okay, so now we're ready. All of this should sort of feel a little familiar to you, and if not, I'm happy to work with you on it, but the reason for the video finally starts here. So we are told that the ratio of U-238 to lead atoms today is 0.31. So how do we think about that idea of the ratio? Well, we would have, let's say we, at one point maybe we have 1 part lead, this is very early on in the procedure, and we have 99 parts 238, uranium-238. Okay? So we would express the ratio of U-238 to lead as 99 over 100, and that would give us the number 99, right? So later on, we might have maybe 50 units of uranium-238. You know, if we did a unit analysis, we looked at the composition of it for every 50 units of lead. And so that would give us a ratio of 1. Well, we're told that currently the ratio is all the way down to 0.31. So we've got X units of uranium-238 to Y units of lead, and that comes out to be 0.31. But also just in the way, and I don't know how the author intended for us to solve this problem, but in the way I thought of this, I'm doing parts out of 100, and so I'm adding to that the other requirement that X plus Y must always equal 100. So I'm now going to solve this system of equations right here simultaneously, and all of this is to figure out what percentage of the original U-238 we now have. Because there's no lead in this problem initially, and there is lead after time, and so that's the ratio that we're going to use to help us compute the original amount of 238. All right, so I'm going to solve this system simultaneously, so we get X is equal to 0.31Y, that's for solving this one, and then I'll substitute that into the second equation, so that gives me 0.31Y plus Y is equal to 100, or 1.31Y is equal to 100, or Y is equal to 100 over 1.31. Okay? And then the next thing I want to do is, well, that tells me how many parts of lead I have, but what I'm really after is how many parts of uranium-238 I have. So X is equal to 100 minus Y. So X is equal to 100 minus 100 over 1.31. And so that gives me parts of U-238. And forgive me, I'm not really comfortable with writing it that way. We put the 238 in front, I guess. Okay, so the last thing is this is parts out of a whole, but what I really want to do is represent it as a percent. So as a percent, I'm going to divide everything by 100, so I get that X is equal to, dividing everything by 100 would be 1 minus 1 over 1.31. And so that's the quantity that I still have remaining. By the way, just so you know, that's approximately 23.6, I guess 66% of the original amount of U-238 is still present. Okay, so it would have been really nice of the author to tell us that 23.66% of the original amount is still present. But that's not how one would actually analyze that in a lab, right? The lab wouldn't, with your instruments, you wouldn't be able to tell what percent of the original amount was present. You could only do the ratio of parts of 238 to parts of lead as you kind of count the different molecules. So this is a more realistic way of presenting the question, but all of this was just this complicated way of arriving at how much of the original amount do we now have, so we can now solve our differential equation for time. Okay. So now, at long last, I'm ready to answer this, what is typically a straightforward story problem, but made complicated by the way the question was posed. So we're ready to solve it. We're going to take our solution from before, which was that y of t was equal to ce to the kt. And we know that I'm going to input this value right here for k, and I'm going to input this value of the original amount for our y sub t. So that is, I'm talking about, we're trying to find the time alpha, where we have 0.2366 of our original amount remaining. So we can now go ahead and plug this order pair into our differential equation. So I've got 0.2366, and actually I need to, because the author doesn't want us rounding till the very end, I've got to do 1 minus 1 over 1.31. That gives me the decimal 0.2366 times c needs to be equal to, that's for my y naught, or if that's my y value, that needs to be equal to ce to the k, and k in this case is the natural log of a half divided by our half-life time, 4.51 times 10 to the 9th, times t. And so now all we have to do is solve this equation for t. So our c's cancel, as they always do, and then we'll take the natural log of both sides. So I get the natural log of 1 minus 1 over 1.31 divided by my k value, which is the natural log of a half, divided by 4.51 times 10 to the 9th, and let's be careful, division isn't associative, so that's the bigger one, and that needs to equal time there. And so now we can go ahead and actually compute time, and when I crunch this in the calculator, I get t is approximately 9.38 times 10 to the 9th years old. Okay. So folks, I think that the hard part about this problem is this middle part here where we figure out how much the original amount we have is remaining. If you had trouble with the earlier part or the later part, that would definitely be a chance to come by and see me, because I'd love to talk more about that. But the purpose of this video was to talk about how we computed the percentage of the original amount remaining. Let me know if you have any questions on that, and good luck.